Hello, in this video I just wanted to talk about and demonstrate the derivation of St. Venant's equation, conservation of momentum equation from the Navier-Stokes equations. So starting off with the x component of the Navier-Stokes equation, we have our unsteady term, the change in velocity over the change in time. Then we have our convective term for each component of the velocity in the corresponding x, y, and z direction, where u is x, v is y, w is z. Then this is going to equal the change in pressure with respect to x times negative 1 over rho plus, which this whole term is essentially the fluid friction in terms of viscosity, plus our body forces. The main assumption we're going to be making is that the friction is going to be taken or incorporated into the body forces, and this is automatically going to render this term to be 0. Assuming one-dimensional flow strictly along the x direction, that's going to isolate these two terms and cancel out the any velocity component that is not in the x direction, leaving these to be 0. Now, assuming a hydrostatic pressure distribution, being where the pressure is going to be equal to rho g h, or delta h if you want to consider the whole distribution. Then plugging that into the Navier-Stokes equation, that's going to leave us with the unsteady term with respect to x, the convective term with respect to x, the plugging in for p delta h rho g with respect to x times negative 1 over rho. I should technically have my body forces on this side. I forgot to add it here. My apologies. So pretend that this is plus body forces f subscript x equals the change in, which this is just a simplification of this, so canceling out rho is just going to leave you with negative delta h over delta x times g plus your body forces. So now we're dealing with only two body forces, being friction and gravity. Looking at a section of a channel in the profile. So here's our bed slope, a length of the channel. This is the water surface up here. Then we have a driving gravity force, W sine theta, and a resisting friction force. So since we're considering the friction force to be along the body, or a body force, the sum of the body forces will be equal to W sine theta minus tau, where W is equal to mg. Then, using the small angle approximation, we can claim that sine alpha would be equal to tan alpha, being where tan alpha is equal to the bed slope. So then sine alpha will be equal to the bed slope. Therefore, that will render the driving force to be simply mg times the bed slope. So then the friction over the channel section or this is what we're going to be assuming, is that the friction over the channel section has a constant head loss over the length of the channel section. So over this channel section, we're going to be assuming that this has a constant head loss per length. So then the friction slope can be defined as head loss divided by L, and that's a like a distance divided by distance, like meter over meter or foot over foot. So that's essentially a slope, and that's going to, so in this we're not assuming that the energy grid line is equal to the bed slope yet. So therefore we can define tau, the friction, to be mg times the friction slope. Then summing up the body forces, we get g times the bed slope minus g times the friction slope per unit mass, because we're dividing out the mass. Then we can assume, then factoring out g, we get the bed slope minus the friction slope times g. Then putting this all together, we have our unsteady term, the change in velocity with respect to time in the x direction, plus the convective term in the x direction, is equal to the pressure term plus the body forces. And then for convention, we're just going to let v equal to velocity and h equal to y for the channel height, plugging that back into the derived equation, and that'll get us the conventional version of St. Venant's conservation of momentum equation. And that's all. Thanks for watching. If you have any questions or comments, feel free to ask and leave a comment. And that's all. I'll see you on the next video. Thank you.